Welcome to everyone, and thank you very much again for joining for the second part of this workshop held by Engineer Haitam Bakur, WASH Coordinator of ACU. I don't want to take more time. I give the word to Haitam, and many thanks, Haitam, for your time, for your professional support. We really enjoy it. Thank you, and the words to you, Haitam.
السلام عليكم الله يعطيكم العافية جميعا.
Good afternoon. How are you doing, everyone? Welcome in this second session for the bombs. My name is Haytham Bakkour, Mechanical Engineering, graduated in 2022, and I'm working as WASH Coordinator for ACU. As you can see, as the first part, we have described about different kinds of the bombs and how we can draw performance scheme for the bumps, and now we are going to talk about the second part. We are going to talk about how we can calculate the TDH. We have two basic information, the flow rate and the value of the compressor, total dynamic arch. Some references are calling it total dynamic arch, and some are saying total head. Based on the reference and resource which we have mentioned here, we need to know how to choose the perfect pump for us. The first stage is to calculate the total dynamic head, which is the total head. As the first stage to calculate that, we need to calculate the diameter of the exact tube, pipe diameter sizing. When we want to choose, we need lots of references, resources, and we need to work on them. As a start, we need to calculate the size of pipe diameter. We are going to explain these equations in the upcoming slides. By the end of this section, the fourth section for total dynamic health, there is an Excel format can calculate this very simply. We need to know these equations like theoretically, but everything is going to be prepared as an Excel file to calculate those. As for the flow, it equals R multiplied V. It is square meter per second. From this equation, if we can have the flow rate or flow value, we can know the diameter or the size if we have the velocity fixed. So it should be between 0.5 and 6, 0.9. It should be closer to 1. We have lots to take into consideration. As the velocity, the speed is constant, so we can calculate the diameter. After having the value of this, then we have this pipe diameter based on D2, which is the diameter of something. Then we have this equation. D is the diameter of the required pipe based on R, which is the space of this section. Then we have the value of D. So we have input, which is the flow rate and the speed. So we can have the diameter of the pipe. So to calculate the total dynamic head, the H total equals H static, the static head, plus HF, which is head losses in pipe. Those are the losses in the pipe, plus HM, the minor head losses. And those losses are happening within the accessories of the network as valves, U-turns, pay, and any other accessory for the network. So we reflect those as HM. We're going to talk about those in detail to reach the total dynamic health. We need to monify and unify the unit we are calculating. We are going to talk about each one in detail, and we are going to see how we are going to use them within the Excel sheet. As a start, let's talk about the total static head. As for the tank, we are pumping the water from and to reaching the upper tank. So there is a total static head here, elevation difference between the two tanks. So the water surface difference between them. So when the first tank is upper or higher than the pump, so we need to take out those from each other. While on the other shape, when we have the tank lower than the pump, so we need to sum those two values between the first tank and the center of our pump and the other tank and the center of the pump, so we can have this total static head as the chart here. So it is total static head. You can notice that we are using many different terminologies, but this is based on many international references and even based on many international companies. We are trying to combine lots of techniques and terminologies, so it makes your life easier. Next, friction losses in pipe, HF. In any pressure network, we have pipes before the pump and pipes after the pump. So the friction losses in all pipes, we code it as HF, and the equation equals 10.71 multiplied L multiplied, and these are the Hyzen-Williams roughness constant. We are using that because Hyzen-Williams is more simple and providing more accurate results. We are going to provide you with a program like an equation, automatic one can provide you with the results easily. So this L is the length of pipe multiplied by the QS, which is the water flow rate, while it is divided on the Hyzen-Williams roughness constant multiplied by D, which is inside pipe diameter. So we have already explained those codes, and but using which units. It is 1 meter, 1 water meter. We are going to explain in detail from where we are getting those values and what are the variables, and we are going to provide you with the automatic equation to calculate those easily. Through this table, we can have the Hyzen-Williams constant value. It is provided by the manufacturing company, or we have it based on the material. So for the plastic, it's 130 to 150. Polyethylene, PE, PHE, it is 140. While for steel, new unlent, it's 140, 150. The more older the pipe, the value is higher. So we are changing the value based on the age of the pipe. And it is, its value is between 130, 150. And those are the losses from inside the pipe. While the other loss is the minor losses in the accessories. and those are within the accessories in the network. Any accessories in the network like valves and others. So those minor losses, Hm equals K, which is a constant. It is a friction losses constant provided by the manufacturing company, multiplied by V, which is the speed, divided on 2 multiplied by gravity. The result, Hm, would be 1 square meter band. So it is 1 square meter of water. It should be provided by the manufacturing company. And we have such tables for the nominal pipe size between 1/2 and 24 inches. And this is the accessory type. So let's see if we have elbow 90 degrees elbow. So we have these losses as 1 meter per equivalent. So if we have 4 inches and the accessory is elbow 20, so we have the length, the equivalent length is 3. This is different than the K multiplied by velocity. I'm going to explain that in detail. We are taking that from these tables. We have talked about the first methodology as K value we take from the manufacturing company and we substitute that, or we can have it from this table. We have the equivalent meter of pipe. If we have an elbow with 90 degrees with 4 inches pipe size, so we have the losses, the equivalent losses are 3. So this is the equivalent. Every accessory within the line, we should calculate its value. So for 4 inches, we have globe valve. So the losses is 36.6. We have it on site, and then if we have gate valve, we have it the losses as 1.4. Then if we have 3 elbows, 90 degrees, so we have 3 multiplied by 3, it's 9 meters. Then we sum all those, and then we have the total value of these losses. And we are going to inform you and in details about those later on. This is why we are converting those losses to equivalent meters, so we can have a unified unit to calculate our losses. So maybe we have 500 or 600 losses, meters lost, so we can compensate for. This is another table from another company. We are going to talk about the software calculating those automatically, and we are going to talk about them step by step. This is providing the water flow rate inside pipe. It's providing the actual pipe diameter, everything. We are going to talk about it in detail when we are talking about the Excel software.
Yes, item, just one question. This table that you have just shown doesn't take in consideration the speed of the water. So it's just a reference. It's not precise.
لا 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 ما سرعة المي ما بناخذها نهائيا.
No, we are not taking the speed of the water in this table. Never. I'm going to explain that later on. Give me a minute. When we are taking into consideration the losses equivalent here, we are not considering the speed. We are going to consider the speed in a different table. This is about the accessory, what is the type, what is the diameter, and what are the losses. It is not about the speed now. Is it clear?
Yes, clear. No problem.
تمام. يعني إن حاليا فقط بناء على نوع الاكسسوار والقطر بناخذ
Currently, it is based on the shape of accessory, the diameter. We are calculating those losses, and then we are applying the speed equation formula. Now we are going to explain about the Excel tool, which is explaining in detail how we are calculating those. Its role is to help the designer. We need to know about the theoretical part, but this software is making our lives easier. We can change any parameter and providing us with the end result. If we have a flow rate, we are putting here the water flow rate. If you have 60 meter per hour, and then the water velocity is 1 meter per second, it should be as much close to the 1. And then we are putting it in the orange cells. It is a manual input, while the others are automatically automatically calculated. So based on the velocity I put, which is 1, I can find the pipe diameter is 5.7. But 5.7 is not existed as pipe diameter. So the software is going to make it up to a holistic number, which is 6 inches. So based on that, the software is going to provide me with the exact actual water velocity, which is 0.9. So if we need to change the diameter of the pipe, so let me change the velocity of the water. So it's 1.2 now. So the software is going to calculate the first value, which is 5.2. Then it's going to make it a whole number, rounded figure, which is 5. So the velocity is going to be 1.3 based on the 60 value I entered as water flow rate and the 5 for the actual pipe diameter. Then the result, actual water velocity is 1.3. This velocity has a reference, georeference or something as reference as for the losses. Then this software is going to take all these data to the losses in pipes, which is this page. So those data have been transferred to this other window. So we have the length of pipes as 1,400 meters. And we have 120 as Hazen-Williams constant, which we extracted from the tables we have based on the type of the material of pipe. So if we have it as iron with 10 years old, so it is between 107, 113. If it is 20 years old, so the percentage is 89 to 100. If it is an iron pipe and it's 30 years old, so the losses would be higher, which is 75 to 90, because it has been eaten from inside, and it has rust. So this is the Hazen-Williams constant and how we can take it. So we put it here within this cell. So I have the first parameter as the length of the pipe. So the second one is the Hazen-Williams constant. Then the volume of flow, which have been taken automatically from the first page. So we are entering as input only the orange cells. So this one is 5 inch as pipe diameter, which have been taken from this page automatically. So I have the friction head losses for each 100 meters of pipe is 1.8. And for the total head losses, we have 25.27 meters. this is very high losses, and I don't want it. So I go back to the first page, I change the velocity to be 1. Then I have the diameter of the pipe is 6, and the velocity of actual water velocity is going to be 0.9. Then I go to losses in pipes. Then I'm going to see that the head losses are 10 meters. So I have won 15 meters by changing the velocity of water. So by each meter I am going to bump, I am going to add an extra power to overcome these losses. So the startup value versus the value I'm getting through the years is going to be different. So those 15 meters we have gained by time, maybe it's going to value the price of all the pipes I've used after 30 or 50 years. We are designing our project for 30 years as average. So as for economical study, we need to take everything into consideration so it can be logical losses and achieving the economical results we are after. So we go back to the question from Mr. Andre. Here we were talking about the length of pipe and those losses in length. So we are adding the minor losses here. So let's go to the minor losses page where we have calculated the accessories. So we go to this table, for example, as I talked, we take from 4 inches. We have a globe valve as 36 meters losses, and we have 4 elbows, 90 degrees, which is 3 multiplied by 4 is 12. 12 added to 36, it is about 48 meters. So we have this equivalence, and we put here, and instead of 1,400, we add that value, 1,448. Then we have the losses. So those losses are not worth mentioning. That's why we are call it minor losses. For some systems, the minor losses are really great and high value. So we need to take those into consideration. If it is like 1,500 or something, so we take 10% of it and add it from the total value. And this is an estimation. The most appropriate is to calculate each losses of each accessory and multiply by the number of accessories and convert it to the length in pipes. And then if we have the equivalent length as 75, we have it here, and we put it as 1,475. And then we have the total head losses, which haven't been changed, but in minor change. What are we having here? What are we getting here? As those are minor losses, there is no problem. Let's go back a little and talk about the last session we talked about, which is the pump sizing. We can see the flow automatically based on the last page is 60. The total dynamic head is 42. Where did he get, where did the software took this 42? It took it from this information. We have put manually the static head, which is 30. Let's talk about it step by step. So we are putting here the flow rate, the pipe length, the Heinz-Williams constant, and we have the population figures here. We should put if we have that. Let's talk about that section. And I put the static head, which is 30, and the losses as we have calculated are 11. So it is about 10.97, so it is 11, almost 11. And we have added 10% as local losses, and the total dynamic H is 42. Is this speed for you acceptable for you? Is it clear for you? Any comments? Would you provide me with any feedback to go slower or something? So let's go back to have the sizing of the pump. Let's talk about the flow rate is 60, while the H total dynamic help is 42. Based on that, we are going to put here the efficiency of the pump estimate as an estimate. So it is 0.75, as the efficiency of pump motor is 0.9. If we know exactly what is the efficiency, we should change here. So we can have here the power of pump in kilowatts and in horsepower. As we can see here in horsepower, kilowatt and power of pump in horsepower, and we have the power of motor in horsepower and in kilowatts. This is the minor power. We need to have more for the motor power, and we need to have it more, but this is the minimum power of motor to be 10.18. Maybe our power, maybe the power is not enough or is not have that capacity in the market. I have finished the first section from the first module of the second session. Please provide me with any feedback, or if you need any other explanation, please come forward.
I think, Aitam, it was clear. Just one question. Automatically, the power of the generator is produced. Is that the minimal power, or is the average power that you need to have for the generator?
بتحكي عن جنريتر. أنا ما حكيت عن جنريتر.
I'm not talking about the generator. Are you talking about generator or motor?
No, the generator. Once you give the power of the motor and of the pump, automatically the power of generator is produced in your Excel.
تمام. حتى حساب.
Exactly. Yes. Even the fuel consumption is existed within this tool. It can even provide you with the consumption rate. This power of generator is based on the type of the control panel. If it is inverter or jump start or star delta, it differs based on the case. So for here, we have asked for soft star panel or autotran. While if it is inverter, it's going to be less. And if it is star delta or dual, it's going to consume more. We have another page to explain this in more detail.
Thank you.
We have this software, and I have developed this, and you can go to the equation. It is an open source tool. You can change all parameters you need, so it can be compatible with your needs. It is an open source tool, and you can change whatever you need to fit you better, and even for the consumption of the fuel per hour. So it can give you even its consumption per hour based on how many hours you are using it per month. Even for the chlor consumption or chlor rate you ask, it can calculate. We're not going to talk those. We are going to talk only about this calculation. You can see how many hours you need to start or to work based on the population of the inhabitants. And we are going to talk today only about equations and losses. Any other questions?
نستنتج انه كل شيء واضح. ننتقل للمرحله. الله يعافيك. ننتقل نكمل البرزنتيشن.
We can say everything is clear now. Let's move to the next module.
هلا نحن رح نحكي عن شيء ثاني.
We are going to talk about something else now.
يعني علوم المضخات بشكل.
The bump sciences are easy somehow, but as it is easier, it is better. I'm trying to simplify every terminology, but I need you to concentrate and focus more, please. We have simplified it as much as we can. You can see our explanation and you can go back to it as reference once and twice. We are going to talk about the system curve and finding duty point. If you can remember, we have talked about the performance curve earlier. We are going to talk now about the system curve for the pressure system, for the bumping system, sorry. As for example, we have this bumping system, we have the withdrawal and the push lines, we have curves, we have valves, we have accessories. So I need to draw the system curve I have. So I need to draw that. I'm going to speak about it in detail. And then I want to cross-check it with the bump curve. So I need the system curve, starting from the withdrawal and going to the end, what we have worked earlier on, which is this, which is total dynamic health. So we have calculated that based to some extent. So we are calculating the flow rate. If it is 40, 50, 60, 30, so we need to draw that curve based on this flow rate. I know it is a little bit confusing, but please bear with me and I'm going to explain everything in detail. In the last session, I have talked about this performance curve, which is HQ curve. This is the scheme which has been provided by the manufacturing company. This line has been provided by the manufacturing company, and this is reflecting the ID of this bump. While the other curve is what we are drawing. It's based on the loss friction and the flow rate. As we have more flow, we have more friction losses. We are going to explain that in details, and we are going to go back to the software, which is going to draw that automatically, so we don't need to waste time in it. What is it? What is it? What are its components? What do we have here? And it's going to be really easy to understand. As we have said, H total equals the static head plus head losses in pipe plus HM, which is the minor head losses. As we know, the HS is almost a static head, and it's related to the tank we are bumping from and bumping to, and it is constant, while HM and HF is increasing as the flow rate is increasing. as the increasing flow is going on, the losses are going on and the speed is going on. So we have this equation, H total equals HS, which is static head, plus FQ, which is Q follower. So it is about the head losses in pipes and minor head losses. So we need to draw this curve. We are going to explain those in simplified way. And the software is going to draw it automatically. As we have said, it is composed of two parts. The first part is a static head, which is HS. It's constant. While the other losses, the other pipe losses, HS and minor losses, is a follower value to the flow rate. The more flow rate we have, the more losses we have. So we can see this chart which we are going to explain later in detail. In this color, you can see in yellow, you can see the system curve. This system curve is composed of three parts. The static head, which is constant, and it changes based on the flow rate. And we have the HS and we have the HS. We have increased the HS here for studying purposes, and we are going to explain that. So we have here this system curve in yellow. It's composed of the HS, static head, plus HS plus HM. I believe it is clearer here. This is the system curve. At the flow rate 50, we have the HS, the static head is 20, and it is constant. The static head is constant. It doesn't change whatever the flow is changed. While for the HS is 8.8 meter based on the casing study, while the HM is 6.1. I have increased that for studying purposes, but those are really minimum and minimal. So we can notice for this curve that the more flow rate we have, and the HF and HM we have, so this system curve is the sum of those values, the three values. So for example, if we have, as we can see here in the table, on the flow rate, let's say, I can't see it here. I don't know why. I'm going to work here. I can't see the table here as I can have many other icons. For 25 flow rate, I have static head as 20. As we said, it's constant. The HF is going to be, if you can tell me.
لا مو زيرو، هاي هي القيمة 13.2. هاي هي 13.2. اروح على اليمين. تمام. تمام، لان انا ماني شايف. هاي معناتها هاي قيمة.
Sorry for this. So you can see here the value, which is 0.7, while the HM is 0.5. And you can see here the H total is 20 plus 0.7 plus 0.5, which is 21.1. So let's talk about the flow rate, which is after that. The next one, which is 25, let's see, 37.5.
نعم 37. تمام. تمام. بغض النظر نحن كل ما مشينا
Disregarding this, as we are going upward, we are having additional flow rate, increased flow rate.
تمام. فكل ما مشينا بهالمنحنى هذا
So the more we are moving with this curve, we can see the flow rate is added. So, and with the added flow rate, we can have additional losses until we have 18.5, which is the maximum losses.
نفس الوقت عم بتزيد
And those HM losses are reaching 13,
فعندي
which is HF. So H total can be equal HS,
المدروسة 20
which is in the studied case is 20 plus 8.8, which is HF, plus the losses for the HM, which is 6.1, and we have H total as 34.9. And we are going to explain in details how the system or the software is calculating it.
عندنا النقاط بالبرنامج لاحقا.
We are trying to calculate that and explain that in details for you. So the H total dynamic heads are the cumulative value of HS plus HF within the pipe as the friction losses in the accessories HM. And we have this system curve.
يطلع عندي الاتش توتال او التوتال ده
And we can have H total here, which is 34.9.
هاي القيمه وين باخذها؟ اذا كانت نقطه العمل هي انا بدي اياها تدفق بدي اياها 50
If we need the
تدفق المطلوب عندي 50
flow rate as 50,
وبروح انا بدور على المضاد
and then we have the value of the pump curve, and we can find that.
هلا نحن منحنى النظام هذا هو رسمناه.
So this is the first system curve we have drawn, and we are cross-checking it with the bump curve, and we have this point here to talk about.
يتقاطعوا بنقطتين نسميها
We have 2 points. We call it the work
هلا مو راح
point.
تفصيل كمان عن نقطه العمل وشلون البرنامج
We are going to explain more about this and how the software is calculating that automatically. Is it clear for you? Do you want me to add anything, to repeat anything? Please come forward.
رح ننتقل
We are going to move
قبل ما نحكي عن المثال
to the example of working point.
برنامج اكسل شلون رسم.
Before that, we are going to explain how Excel software have
وعليكم السلام ورحمه الله
done
وبركاته.
this. Come, Abu Munzer, I have a question. Based on the local losses, why there is a change of its loss based on the rate or flow rate? Some of our colleagues didn't get it maybe. Can you tell us why it's changed based on the flow rate? I'm going to talk about it again.
اللي حكينا عنه مش
Those are the minor losses, HM, local losses. It is
تزداد طرديا مع
related and it is going based on the velocity. The more speed it has, the more losses we have. And the speed is about flow rate divided on the surface.
مربع التدفق. فانا لو
So
تدفق
if we have more flow rate based on some value, so we have the losses have increased more. If the speed is doubled, so the losses are quadrupled. As I said, some people or some colleagues who are newly graduate, maybe they have this question. This is only clarification. Thank you. Much appreciated.
احنا بدنا نرجع على البرنامج نفسه
So let's go back to the software itself
duty point
and let's talk about the duty point or the system curve.
شيل اللوحه هاي من عندي
Can I take that panel to other place? It is moved now. Thank you. It was bothering me.
برنامج
So now for this table, the software has took those values automatically and calculated it and drawn the system curve, the duty point. It has calculated that based on the value I put here in the length of pipes. I put this value plus the equivalent length, then the software has calculated that automatically as a maximum point, a maximum value, and replaced it with the local losses. Let's see it practically. We have this panel, this table. I enter those values manually. If I have this flow rate as 30, we enter this from 0 to 50 or to 250 something. Those values I enter regarding the flow rate and the system based on the length of the pipe and the static head and the pipe diameter and the Heisenberg value. So the software is calculating those losses and everything automatically and drawing the curve, the system curve, which is here in red. You can see the more Q rate value we have, the flow rate value we have, the more losses we have, HMFM. And then we have the total dynamic head here increased. As I put the mouse at any point, it provides me with the data you can see on the screen. It provides me with the values of the flow rate and the total head. So if the flow rate is 40, so the total head is, total dynamic head is 35.7. Why the flow rate is 50? So the total head, total dynamic head is 38.6. I believe it's easier for you. When the flow rate is 0, the total dynamic head equals the HS, which is 30, the static head. Is it clear, guys? Any question? Can you now tell how this system curve has been drawn? So if I want the duty point, I can give the software the value of the H, and I put the Q rate, I put the H bomb for the bomb, and it's draw the duty point and the in blue, while the system curve is drawn automatically. So for this bomb, the duty point is Q rate is 40, the flow rate is 40, while the pressure is the 37, the compressor. Any question? We can explain in theory later on about the duty of duty point. I'm going to provide you with an example about this. Do you have any questions? So we are going to talk about how to find the duty point for a bomb based on the calculations we have. So I have here for Grand Foss and some other types. I went to the website and they have changed a lot here. So I'm going to explain that in theory on the chart, and then we are going to look at the changes they have done on the website. Then we can explain better. So for now, we are going to explain how to find the duty point for handstand examples, and we are going to explain our grand force.
فالمثال على الشكل التالي
The example is
مطلوب إيجاد مضخة المناسبة وإيجاد نقطة العمل وذلك للحالة التالية.
and this is for the following case.
116 متر عمود ماء.
The TDH is 116 MH20 MH2O. The static head,
التدفق 30 متر مكعب.
it is 30 meters.
متر.
The geographical altitude difference static is 100 meters. So we are going to find the bomb that can cover this power and this needed values. So the TDH is 116, the flow rate is 30, while the static head is 100. In general, when we are trying to look for a bomb, we are going to the catalog and look at the flow rate. For the Bunsen generators, I can see here based on the 15, 30, 80, and we have a series of types of bombs. For those series, we can take the flow rate as of 30. So we have the flow rate is 30 cubic meter, and the 116 static head. No, so it is a immersible bomb. So it is between 0 and 20 stages. As much more stages we have, the value is increased with the flow rate. So when we had, for example, 7 stages, we have the curve as this. When we had 14 stages, so the curve was looking like that. So when we have it like this, we need to increase the stages so I can increase the rate of the bomb. So if we have 30 flow rate in red, in addition to 116, which is 116, and we have this point. This point, we can find the nearest curve for this, and we build on it. So we can see that this curve is better for a curve, the duty point needed, which is 16 stages. So the stages are 16. And the horsepower is 20. So I go to the additional table from the catalog. So I have this curve in general. So I have the total efficiency we talked about at the last session. So we choose our bomb is the closest to the highest efficiency rate. So we don't use the bomb at this end or that end. We need it within the blue scope. This is the best scope and range we need to choose. So it is not okay to start or to engage our bomb unless it is between 70 and 110, which is the flow rate. So we don't need much losses in this area. So I need another bomb, or we can go to another company if we couldn't have the maximum capacity and efficiency. So the efficiency here is going to be 87%. So the losses in this pump would be only 13%. And those losses are lost costs in addition to less in the age of the pump, because it is about some issues created by the shaft or the impeller. So we are causing shortage of the pump if it is not providing its good rate in its efficiency range. As you can see, it is 75 or 78% the efficiency. And for Bansan, we can see the power for one stage is 0.85 multiplied by 16. It is going to be 13.6 kilowatts. This is the power. We are not going to depend on that shape only, but we are going to refer to the other tables by the manufacturer company on other page. So for the 30 flow rate, based on the stages we have 16, I'm going to show you the catalog. Maybe I can explain more or in simple words. So 16 stages I have. So the kilowatt is going to be 15. The HP horsepower is going to be 20. The dimensions, the total length with the pump is going to be like this: motor length, pump length, diameter of the motor, diameter of the pump, which is based on the manufacturer company. And we have 3 points here. We have the weight of the parts, the motor weight, the pump weight, that the total weight of the pump and the motor. Exactly. We can go to the catalog to explain better. We are going to talk about our choice from Grandford. I planned to explain from the website, but it has been changed. So I'm not going to do that. I'm going to talk about this. Based on Grandford, you provide the flow rate, and automatically it provides you with the type of pump they have, and you can choose which one you need. Based for example, based on this, we have chosen this pump based on the number of the pump, and we are going to explain later in details how have we chosen this. So we can see the curve here, and we can see the parameters of this pump. As for the flow rate, we have it as 30 and 116. So Grandford is going to draw this automatically for the system curve. We are providing the statistic head and the system head. So based on a special algorithm, which is the same algorithm we have calculated for the HM and LM and the velocity. And it's providing me with the values here. As for the pump we have chosen, it's providing me with the duty point exactly as I need, but it is not like this. This is in zero condition. Maybe it's going to be a little bit more or less, and then we can choose the best for us. So as for the 116H, and the rotation of our pump is going to be 3,500 RPM, and it is by water. Pump liquid is water, and this is liquid temperature during operation. So we can have here.
Assam, there is a question, I think, on the chat.
No, it is not. Someone is leaving and he's sending an apology message.
Okay, sorry for that.
تمام. فنحن هون يعني مثل ما حكيت لكم للاسف انه ما عم بشرح الموقع.
Unfortunately, I'm not explaining on the website directly because it was really not okay that they have stopped this website, and I was working on it for years now. So B1 is the motor, B2 is the pump. Based on the duty point we have witnessed, we can see the curves here. we can have the value of the motor, which is 15.44 kilowatts, while the pump value is 17.3 HP, and NBSH equals 6.21, and this is provided by the manufacturer company. So if the pump is in a well, so the length should be 6.21 centimeter. If the water level is above the water, more than this, there would be electrical shock or something. We're going to explain about that later on. I can see here NBH, that's regarding impressive. Do you have any question?
Go ahead.
هلا نحن صرنا يعني تجاوزنا الساعة و10 دقائق، فأنا رح ننهي.
We have come over 1 hour and 10 minutes. I'm not going to talk about electrical static or something. Maybe we can finish here and we can open the floor for questions, and for the other session followed, we can go into details more, and we can explain on the website of Grandfos and how we can choose our bomb, and that would be much beneficial for our colleagues. We have come over 1 hour and 10 minutes for our session, and we are going to give the floor for any question, any debate. Please, we can re-explain, we can answer your questions. Please, the floor is yours. Many thanks for you, Haytham. I have to leave, sorry. Bye-bye. Thanks for you. If you have any other question, guys. Andre, do you have anything to provide?
No, I think, Haytham, I think it was very clear. If there is question, please take now the opportunity. Or think about. Meanwhile, I will thank Haytham a lot about this presentation. I think it was very clear and very useful. This software definitely, it's a big help for any WASH person who has to develop a pumping system. This Excel sheet, Excel file will be linked to the YouTube channel, of course, and like Haytham was saying, free available to everyone.
Thanks a lot for you all. I hope it was beneficial for you all. And please come back to it as much as you need.